Swayam Prabha. Digital India. Educated India.
If these two are not correct, the other case could be we are going in the wrong direction or the function value remains same. In that case, we want to search in the reverse direction. For that reason, we are saying for all other cases, we want to set my S value, which indicates the step size, in the negative direction, and then we go to next step. If we are not any conclusive, we can actually terminate at this point and look for another start point. So let us look into what happens in the step 6. So this is the point where we know our direction, we also know our start point, and we also know our step size. So in this direction, we want to find points with respect to the initial guess point using the criteria of the step size and using the criteria of my iteration. So my iteration had indicated as I equal to 3. So my first point is going to be I minus 1, which is 3 minus 1 is going to be 2, 2 times S. So in the first iteration, or after completing, if we consider this as a first iteration, this can be iteration 2. So in iteration 2, my x3 is going to be x1 plus 2 times my step size. And at this particular point, we are finding out the objective function value. And once we find out the objective function value, we would like to compare the objective function value with my previous point objective function value. So in the second iteration, my previous point is fx2 and my current point is fx3. So we are comparing between these two, and as I said in the step 5, if it is a minimization problem and we find that the direction we are moving is still good, which means my function value at the new point is lesser than the previous point, then we should increase our iteration number, means we are increasing our I value from 3 to 4, and then again go back to step 6 where we'll be in iteration number 3. If it is a maximization problem, that means at the new point our function value are expected to be increasing, and if it is so, we are again increasing our iteration number from, or our I value from 3 to 4. If none of this happens, we have reached to a point where the function value is again going in the opposite to the optimum point. So which means we have reasonably come closer to the optimum point, and hence we can stop there. For that reason, we are saying go to step 9. In the step 9, we are reporting the present point and the previous point as the bracketing point of the optimum value, and using this we'll take it forward for further refinement in the other methods which we'll discuss later. So let us now understand this method in a graphical way. If we have a minimization problem, a function, particularly unimodal function, is going to look like this. In this function, if we have started some point here and we say want to test the direction, we find that if we go in this direction, our function value is reducing, means our direction is right. So we can take another step of same size and again check our function value. Again we are finding that this function value is better than this function value at this location. So this point is good. We can move in this direction further of the same step. Then we come here and again we are finding our function value at this location is better than this location. So we are improving. We can take another step of same size, and if we are reaching to a point, now we start finding this point, the function value is equal to the previous point function value or actually worse than the previous point function value. That means we have reached the termination point, and we can report these two as the bounding or the bracketing point within which my optimum point is going to lie, or within which my objective function is going to be minimum. Likewise, if we take the maximization problem, it is going to look like this. And let us start from the different side of the problem. Suppose if we guess an initial point which is here, and our positive direction search is this. So if we take a step of s length and we reach this point and we find our objective function value at this point is reducing for a maximization problem, then we know that we are going in a reverse direction. So rather we said at this point we should change the sign of my search direction to the negative and go in this direction of the same amount and see my function value. In this case my function value is improving compared to the previous point, which means now I am in the right direction. I use this direction for further search of equal step. So I move to the next point, which will be here. Again I find out this point is better than the previous point, which is here. So I can go further of the same distance, which is going to be here. Now I start realizing that my objective function value is either equal or less than the previous objective function value, and if we find so, then we can stop here and we can say this is my bracketing region within which my optimum value, in this case the maximum objective function value, lies, and we need further investigation to find out that particular region. Now let us look into an example to understand this method. In this example we have a function which we need to minimize, and in this function we are starting from a point 0 with a fixed step size of 0.1. So if we want to start this way, let us look into the solution. We know our function value, our start point as x1 equal to 0, then our corresponding objective function value is going to be 0. We know the step size 0.1. In this case let us assume that we are going in a wrong direction. So suppose we had gone in a negative direction, my second point x2 would have been x1 minus s, which is going to be negative 0.1, and the corresponding function value would have been 0.16, which is in this case increasing compared to the function value of the initial guess point. It indicates my search direction is wrong, so I should be changing my search direction, and the changed search direction is going to be the positive direction where I need to add rather than subtracting the search direction. Now let us look into the solutions obtained step by step. In our first iteration, we checked the function value at the x1 point and we found out it as 0. Then we move to the, we can say, iteration 2 or the next step, where we'll pick the second point, which is my x2, and that x2 was 0.1, and we found out the objective function, which is actually improving. My new point is better than the previous point, so I am setting the counter, or I am increasing the counter by 1, and then I move to the next point, which is going to be 0.2. My function value is negative 0.26. Again, we are finding out that my function value in the new point is better than the previous point, hence we are increasing the counter, and this process goes on till we reach a point where we find that the objective function value at the new point is no longer improving, it remains same. At this point, we can say we have reached the point where our objective function could be, so we are saying that we need to stop here, and we are reporting our optimum point to be between 0.7 and 0.8, and the function values could be somewhere very close to 0.56, the negative value of 0.56. So this one, if we want to represent graphically, our function values, we started with 0, we moved in the positive direction of 0.1, so this is my 0.1. At this point, our function value is this, which is better than the previous function value because it is reducing. So we are taking the same amount of step, we are moving to 0.2, and then again we are finding out our function value is improving, so we again take the same amount of step, and then we are finding our function value is again improving. So this way, once we reach 0.7, then we took one more step and found out that our function value remains same. At this point, we could have gone one more step here, and we may find that the function value is increasing, and we could have bracketed between this and this, or this and this, or this and this. In this particular problem, we chose to bracket it between this and this, which can be further investigated for the actual optimum point. Now in this method, you saw that we are taking small steps to move towards our optimum value. If our guess, the initial guess point, is close enough to the optimum point, we can easily reach to the optimum point, or proximity of to the, or close to the optimum point. But if our initial guess is too far, then it would take many iterations to reach closer to the optimum point. This can be avoided if we actually use the accelerated step size method. So here we'll be discussing about the unrestricted search with accelerated step size. This method, we are actually using the step size which changes at each iteration. In order to reach to our optimum value, or very close to our optimum value, we can increase the step size at each iteration. One of the way of increasing the step size could be by doubling the step size. So if we can double the step size, we will be reaching closer to the optimum point faster. Apart from this change in the step size, the method remains same as the fixed step size. Let us see through an example how this method works. So we choose the same example where we need to minimize our objective function, and we are starting from a point 0. In this case, we are choosing a step size even smaller than the step size we had in the earlier case. So if we start again, our objective function is this. We are starting from 0. The objective function value at that point is 0. Our initial step size is 0.05. Again, if as a check, if we start in the negative direction, we will find that our objective function value is increasing from our present objective function value. So we should actually reverse our direction and see whether we can reach closer to the optimum value. So here is the step-by-step process. In the first iteration, we found out the objective function value. We already know our search direction. So we found our second point as 0.05. We found the objective function at this new point is better. So we are increasing the counter by 1. Then you will see that my next step size is going to be double of it, which is 0.10. So my next point is 0.1, and there again the function value is better than the previous point, which is negative 0.073. So we are again increasing the counter by 1, and now again my step size has doubled, which is 0.20. At this point we are finding out that my objective function value, which is negative 0.260, is better than the previous objective function value, which is negative 0.140, and hence we are again increasing the counter, and as we move we reach to a point where we find that our objective function value improved up to this point, and any point further or the next point it is rather not improving. So we stop at this point and then we report our optimum point. So my optimum point is going to lie between 0.8 and 1.6, and my optimum function value is going to be between negative 0.56 and positive 0.16. Now let us look into the graphical representation of this solution. We started with a point at 0, and then we moved a step s from this point to this 0.05, and we found the objective function value is improving. Then we increase the step by another. So from the original start point we have the distance 2s. So at this point we are again finding out the objective function value improves compared to the previous objective function value, which was here. So we doubled the step. Now it is 4s from my start point, which is going to be 0.2, and we are seeing that the objective function value at this new point is better than the previous point. So it becomes 8s, which means from the initial point it is 0.4, and we are seeing the same thing. So from 8s it will become 16s, which will be the point at 0.8, and again we are seeing improvement in the objective function value. Now from 16s it will be 32s, and my next point would be 1.6, and there the objective function value is actually increasing, and hence we are stopping here and we are finding out that the bracket or the optimum point is expected to lie somewhere between this 0.8 and 1.6. So in today's lecture we understand that certain real world engineering problems are difficult to express as an explicit function of the design variables. Then we also saw that there are other ways of solving such problems, and one such method is the numerical methods to solve the optimization problem. And in the numerical optimization methods, we started with the elimination methods, and within the elimination methods, today we discussed about the unrestricted search method using fixed step and as well as accelerated steps. A few things to note about these methods. My objective function is supposed to be unimodal. The two methods which we discussed specifically in today's class, we also need to be careful with our initial guess and the step size. As I had indicated during the lecture, that if my initial guess is too far off from my optimum point, then it takes longer to get closer to the optimum point. Similarly, if my step size is very small, to increase the precision of the bracket or the region where my optimum solution lies, then again it will take longer time or many iterations, a lot of computational steps to reach closer to the optimum point. In the next class, we'll see a few more elimination methods which can be effectively used for bracketing the optimum point or the optimum solution. So with that, thank you all. See you in the next class.